Hey everybody, in this video, for completeness sake, I want to present the expected value and the variance for a continuous random variable. Now this is a little bit harder than finding the expected value and the variance of a discrete random variable that we presented in the previous video. In the case of a discrete random variable, let me remind you, if you have a random variable, if x is a random variable, what it does is it only takes finitely many values, x1, x2, and so on, xn, each one with certain probabilities. Let's say with probability p1, with p2, with let's do it like this, with p of x1 equals p1, p of x2 equals p2, where p1, p2 are just numbers, with p of xn equals pn. And remember how we calculated the average, the expected value of a distribution, as the probability p1 times x1 and so on. So p2 x2 plus pn xn. It was very straightforward. And similarly, we calculated the variance of that same random variable as just p1 times x1 minus e of x. We decided to call it as mu square, plus pn times xn minus mu square. Sorry for that. So that's just a mu. And it was very straightforward. In the case of a continuous random variable, such as the normal distribution or the uniform distribution or any other distribution for that matter, life is a little bit more difficult because we need to use calculus techniques to calculate the same result. Because in the case of a continuous random variable, the values that x takes is infinitely many. It's a continuous stream of outcomes, right? So for instance, when we say x is a random variable with a uniform distribution between 1000 and 2000, we mean that it is 1000, 1000.001, 1000.002, and all the way to 2000. There are infinitely many values. In those occasions, obviously, we use calculus to solve these type of problems. There are some concepts, some of the, for instance, let me just give you two examples, which are the obvious ones. If you have a uniform distribution, uniform distribution, which is a normal, which is a continuous random variable. So suppose that your uniform distribution says that the values of are between, let's say, 2 and 6. So because it's a distribution function, so suppose this is the uniform distribution function, the area underneath that distribution function should be equal to 1. So as a result, the height here, because the base is here, the base has a length 4, so this one, the height should be 1/4. So as a result, for instance, if you have such a uniform distribution, all outcomes are equally likely between 2 and 6. So if someone says, what is the probability that the random variable is, say, between 2 and 3? Well, that's easy. From the picture, we can see the picture here gives you the probabilities here, right? So the probability density function, and then this one is your random variable x. So it's asking for 4, 3, 5. Okay, so this is where, oops, sorry for that. This is where the 4 is. So because it's asking all the outcomes, the probability of the x being between 2 and 3, right? So it is really this area. But because the whole area was a 4, that area will end up being just 1/4, right? So for instance, this one, the answer would be 1/4 by just inspecting the picture. So for example, what is the probability that the area between 4 and 5? That one is also easy. So 4 and 5 would be this area between those two numbers. And because the whole thing is a 1, so that one would be 1/4 as well. Or for instance, what is the probability that x is strictly greater than 3? Well, that one would be 3/4, and so on. Very straightforward. The same thing applies for the normal distribution. So the probability distribution for the normal distribution, this is also a normal probability distribution. It is also what do you call it? A continuous random variable. Suppose that we have a standard normal curve, something that we looked at last week as well. Oops, so this picture is pretty messed up. There you go. So suppose that the question is asking, so we have a normal, x is normally distributed with a mean of 0 and standard deviation 1. So if the question asks, what is the probability that the values of x are between -1 and 1, given this probability function, we call this usually the probability density function. All right, so it's kind of different than the probability function in the sense that probability function is usually associated with the cumulative distribution function in a sense. So okay, so this is a density function, p of x. Usually this is represented with a lowercase p. So the question which asks for what is the probability that the values of x are between -1 and 1, what we can do is last week we just learned how to use the Excel. Basically using the norm.inv function we can identify the probability of such an interval, which I believe, if I remember correctly, the answer should be very close to approximately 68%, something like that. All we do is we looked at the area to the left of 1, and from that we subtract the area to the left of -1, and that should give you the desired answer. And obviously for this one we use the norm.inv function. Similarly for this one we use the norm.inv function, something that we learned last week. So this is very easy. Now let me, these are obviously some well-known distributions, but how about any random, any a normal continuous random variable, any not well known like uniform or normal distribution? Let me give you the following example, and this is just for those of you who have some sort of good calculus skills, so it will be a fun exercise. So suppose that example, we are given the following probability density function. Say the probability density, so we have a random variable, call it y. Y is a continuous random variable with the following, with probability density function, say f of y is given like this: c times, where c is a constant, y square for y between 0 and 2, and elsewhere it is just 0. All right, and f of y is simply equal to 0 elsewhere. So given this, we want to find what should be the value of c. First of all, what is c basically, first of all, and second of all, once we find c, I want to find the expected value of this random variable y, and then the variance of that random variable y. So like I said, we will end up using calculus techniques to solve this, because that's the standard method for dealing with continuous random variables. But once we see the theory, obviously at the end we want to build Excel models to do it, but I wanted to make sure that I just show the theory at least once so you guys can have an idea how it's going to work out. So because we have our probability density function f of y as c times y squared, it turns out that the area underneath that curve, by the way, that curve will look like this. So if you have our random variable here, and the probability density function, apparently we are told it is 0. Anything before 0, it is 0. Anything after 2, it is also 0. But at 2, between 0 and 2, 0, 1, 2, it follows this function. But this function is just a parabola. It's something like this. So something that we are familiar with. So the question is, of course, we don't know the value here. The value here would be c times 2 squared, which is 4c, I guess. So all we want is to make sure that the area underneath this curve should be equal to 1. Does that make sense? So the area we want underneath that curve to be equal to 1, but that's easy using calculus. Okay, so the expected value as a result Well, so before the expected value, we need to calculate the c. So the probability underneath that function must be equal to 0, the area I should say. But area is easy to calculate in calculus just using integration. So do we have the integral? Okay, so this function is a piecewise defined function. So between minus infinity and 0 for the values in the horizontal axis, the value of the function is just basically 0 dy plus for the values between 0 and 2, the function takes this value, dy, and then for the values between 2 and infinity, again it is 0. Does that make sense? So these two will just cancel, so we will be left with this one. So the c will come out of the integration times the integral of y squared is just y cubed over 3, and we will just plug in 0 and 2. So that is just, let me just do it here. So let me just factor out the c over 3. So plugging in 2, we get 2 cubed, minus plugging in 0, we get 0 cubed. And finally, this is 8 over 3c. We need to make sure this is equal to 1. So therefore, this implies, because it's equal to 1, c is equal to 3 over 8. Awesome. So now we know the full shape of the function. So the probability density function here is 3/8 y squared for y between 0 and 2, 0 y 2, and 0 elsewhere, 0 elsewhere. If it's less than 0 or greater than 2, yeah, that's it. So maybe I can put this bracket here and then make sure this, yes. Let me make it. The handwriting is not that good. Let's just do it again. Else, where? There you go. And let's put that line over here. Now we can answer the second and the third question. What is the expected value? And what is the variance? Well, the expected value, E of y. Again, this is a concept from calculus. It turns out to be, we can calculate it by just taking the integral again, expectation using integration, I should say, and it's again a simple concept. For instance, all we will do is the following. Let me first write the general formula. The general formula says y times f of y dy. Now compare this with what we did previously. Here, the formula that we used is just f of y dy between minus infinity and infinity. So we just realized that this function can be split into 3 parts because it's a piecewise defined function before 0, between 0 and 2, and after 2. That's exactly why we did split it into 3 parts. But you guys can see that in this definition there is no y here. It's just one f of y. This one is y f of y. All right, so the rest is just again splitting it into 3 parts. But the first and the third part are 0 because that's the way the probability density function is defined. So the interval of interest is between 0 and 2. Y times f of y itself, we just figured it's 3 over 8 y squared dy. But that is just, again, let's just do it one more step here. We can just factor out the 3 over 8. So we just have a y cubed dy, and now 3 over 8. So y cubed, the integral of y cubed is just y to the 4 all divided by 4 between 0 and 2. So that is just 3 over 32. Plugging 2, we get 16. Plugging in 0. And finally, this is just 3 halves, I believe. Wait, is that correct? 3 halves. Yes, that's it. That's in average. And it kind of makes sense, right? So because most of the distribution is like the area. So basically what this means is the median is right here, the midpoint. So the area on this side, this is 3 halves. And this side are kind of equal to each other in a sense. All right. So that's a pretty neat deal. And finally, we can also calculate the variance. The variance will be a little bit messed up, but a bit more calculation, I should say. The variance of y will simply be the expectation of y squared minus the expected value of y squared. Well, the second part, we already got it, so it's 3 halves. Just the first part is, okay, so let's just calculate the first part next. But that's easy. Again, integration, I don't even need to check, so actually, okay, let's just do it in 2 steps. Y squared f of y dy, but again, because anything outside 0, 2 is just 0, so it's really between 0 and 2. Y squared 3 over 8 y squared dy, and that's pretty much it. So 3 over 8 integral 0 to 2 y to the 4 dy, and that is just equal to 3 over 8. Y to the 4 is just y to the 5 over 5 from 0 to 2. That is just 3 over 40. Plugging in 2 to the 5 is 32, 0. That is just a 0. So that's just 4/5, 12 over 5, if I'm not mistaken. So, which is 2.4, I think. Now we can plug it in here. So we have 12 over 5 minus 3/2 square. 12 over 5 minus, well, okay, so let's just write it as a decimal, I guess. 12 over 5 is just 2.4, minus 1.5 squared is just 2.25. The difference will be just 0.15, will be the variance of this continuous random variable. And like we said, so this is the mean, or the expected value, the average, and this one is the variance. Hopefully this was kind of informative. I just wanted to provide this example for those of you who have good calculus skills. Like I said, you guys can totally ignore this question if yeah, it's just an extra question that I wanted to share with you, just in case, because know that random variables are two types, and usually these type of continuous random variables, we try to deal with them as much as we could using Excel models, so that we try to avoid using calculus as much as we can. But ultimately there might be occasions where this cannot be avoidable, especially those of you who are interested in a career in actuary, as an actuary. So you will have to learn how to take integration and differentiation. So that finishes this example.